Hi, welcome to Knowledge Base. In this video, I'll explain how to generate this pulse width modulation, which controls servo motor. So the key is you have to generate the delay. Okay, the delays of 1 millisecond and 19 millisecond, all these things. So for 2 millisecond and 18 millisecond, all these things, basically the variable delay. There is a few things which you have to understand if you are using PIC18 microcontroller. Okay, PIC18 microcontroller uses 4 oscillator cycles for one CPU cycle. That means each CPU cycle consumes 4 oscillator cycles, which oscillator cycles in the sense the crystal what you have connected. That means if you have connected 4 megahertz crystal, okay, so if you have connected 4 megahertz crystal, CPU clock is 4 divided by 4, which is equal to 1 megahertz. Sorry. Okay, so if you are using 8 megahertz here, then your clock cycle is CPU clock is 2 megahertz. If you are using 16, it is 4 megahertz. Okay, so you have to divide this oscillator clock cycle divided by 4 to get the CPU clock cycle. Okay, so each instruction cycle is equal to, here I mean like that is why I told use 4 megahertz. In my previous video I had explained use 4 megahertz so that the calculation becomes simple. Okay, so here it is, one instruction cycle is equal to 1 divided by 1 megahertz, that is 1 microsecond. Okay, so 1 microsecond is an instruction cycle of the CPU. Now if I waste one cycle, instruction cycle is also called as ticks. Okay, if I waste one tick, that means I am wasting 1 microsecond. To generate 1 second, I have to waste 1 million microseconds, correct? So if I waste 1 million ticks, okay, so microseconds in the sense now the ticks is equal to 1 microsecond. If I waste 1 million ticks, I am generating 1 second. Now if I want 1 millisecond, I have to waste 1000 ticks. So 1000 ticks is equal to 1 milliseconds. To generate 2 millisecond, I have to waste 2000 microseconds. Simple. To generate this delay, there are two ways, that is using timers. Okay, timers is peripherals inside PIC microcontroller by which you can generate the delay or you can calculate time and all. But anyway, these things I'll take later. I mean like in future videos I'll cover those things. Right now we are using nope instruction. Nope in the sense no operation. That means we are wasting the cycles. Okay. To call this, instead of writing our own for loop and wasting this nope instructions, C compiler, that is XC8 and C18 compilers, they have inbuilt delay functions. Okay, delay functions like delay 100 ticks, delay 10 ticks, and delay 1k ticks, delay 100k ticks, delay 10k ticks also. Okay, so the full range of I mean like delay is available, so we'll use that. Internally the function is using the same, they are wasting cycles by using nope operation. Okay, so this is about the theory, how it is calculated in different microcontroller like ARM and AVR or Atmega, I mean like Atmel. There you don't have to worry, they will be working at same clock speed whatever you have connected. Then you have to waste 4 clock cycles, so the calculation remains same. You have to find out instruction cycle and waste so many cycles to get the delay whatever you are required. Okay, let's switch to MPLAB-X. MPLAB-X IDE is from Microchip, and this is the IDE which we'll use to program PIC microcontroller. Okay, so let's look at how to create these projects and all. Very simple. You will go to project, new project, and Microchip embedded standard project. Next, there are some videos which explains these things elaborately. Okay, and I'm using PIC18 F4550, and this is it. And then I'm using PIC3 is my programming tool, and this is my compiler, and I say next and project, save all those things. Very simple, and you'll get a new project here. Okay, that is it. Very simple. Then you'll go to source file and new C file. That is how you generate this file. Okay, so I have already put an LED on this file. Okay, C file, which where I have already written. Okay, so let me increase the font size, because when I render it may not be visible. Sorry. Okay, so this is the program. Very simple program to generate the delay. We have to include this xc.h file, header file for pre-processing all those things, and then delays.h, because we are using delay functions to generate the delay. And this program is basically to generate 1 second delay. Okay, then these things are configuration registers which you had to set. Like oscillator is high speed and there is no PLL division, and internal external oscillator switching, and power on reset, and all those things I have configured. Basically, if you see, if you go to window and pick memory views and configuration bits, here you'll get the information, like how to set all these things and all. You'll come to know here. Okay, so you can always configure here, and you can actually generate that code here itself. So after setting up all these things, if you click on generate the code, it will generate this. So all you have to do is like copy and paste it. But anyway, right now I'm not worried about that, because I already set the minimum required configuration registers. Okay, and all others are left as it is. Okay, so that is it. So for beginner, don't worry, just copy and paste this part. Okay, and you will learn all these things as and when you start working. So I can connect actually 4 megahertz crystal, and I can make it to work at 8 megahertz by just changing it to 2 here. Okay, those things you'll learn later. Okay, so this is the main program, and I'm assigning this thing I'm not using anyway. So first thing is I had to set the direction of the register. I mean, like the port D. I mean, the register is stress D, and 00, that means output. So all the pins of port D is set to output. Okay, so if you want to individually address them, you can always use something like this, and individually you can make it as 1 and 0 and all those things you can do here. Okay, or else directly calculate the hex value and write here. Then the important thing is oscillator configuration. Oscillator configuration, this I have noted from the, I mean, like if you go through the data sheet, you will come to know why these each and every bit is set, and why is this set like this. That means why is this number 0 1 1 0 1 0 0 0, why is this you will come to know. Basically I have said to use the oscillator, I mean, like crystal oscillator as primary clock source. That is the meaning. That is what I have set here. Okay, and no internal oscillator is been enabled. So that is the meaning. I went through the data sheet and said this. So right now what it is happening is our 4 megahertz crystal, whatever I have set, I mean whatever we have connected in the hardware, that is what it is using as the primary oscillator. Okay, that's it. So next it is a simple routine, while 1, that is infinite loop. Port D is equal to 1111, that is FF, and I am waiting for the 1 second. 1 second here, if you see, it is delay 10k ticks. That means this function is called 100 times. So 100 into 10k, it gives you 1000 k. That means 1000 k. So that means 1000 into 1000, which gives you 1 million. Okay, so that is how it is. And then Okay, let me show the calculation again here in case if you are confused. Um, okay, so this is what I'm talking about. This is 1000 into 1000. Okay, so that means 1 million microsecond. Let me remove the pinning here. Okay, that is what I'm using to generate 1 millisecond, I mean like 1 second delay. So then I'm making port D to be 0, and then again I'm generating 1 second delay. So this is the simplest code to start with. Okay, now if you remember the calculation, let's go to the servo part. Okay, this is from the other uh, I mean project. Okay, so I have already opened it. So all these things remain same. I have to use delays.h, and I can actually show you the delays.h also. Okay, so if you see here, there are a lot of functions like delay 1 tick, delay 10 tick, delay 100, 1k, 10k, and 100 is basically no, I think 10k is the max. Okay. Okay, so main here is the program starts, and same thing I'm using trusd, and it is actually set to output, and then oscon to use the same oscillator what I have set. And then before going with this for loop, let me explain this part how it is working. So port D is equal to LEDs. That means I have set LEDs to be 1111. That means all 8 pins of port D is set to 1, and then I'm generating a delay of what is this, 100 ticks. Okay, so now delay of 100 ticks I times. Okay, so it is called number of times which is written in the parenthesis. So I is 10 initially, so that means this delay 100 ticks is called 10 times. So 10 into 100 ticks is equal to, you will get 1000 ticks. 1000 ticks is basically equivalent to 1 millisecond. Okay, so 1000 ticks are microsecond. Because of this 4 megahertz, the clock has come down to 1 microsecond. Okay, anyway, so 1000 ticks is equal to 1 millisecond. That is what it is. So that is what I'm generating here, and then I'm switching off. Okay, so I'm toggling LEDs and making this port be as 0, and then I'm setting the delay of 19k ticks. Okay, 19k ticks. That means oh sorry, that means the see, after this positive pulse what I had generated, I had to generate 19 milliseconds delay. Okay, at which this pins are 0. Okay, then again I am toggling the LEDs, and again I am setting LEDs to port D. This I am repeating 50 times because I have told in the sorry, in my previous servo explanation, I have told this pulse I have to send 50 times. Okay, for 1 second I have to send this pulse for 50 times. Okay, so that is how that is what it becomes. This 20 millisecond of delay, I mean 20 millisecond of the pulse, it repeats 50 times for 1 second. So I have to send this for 1 second continuously for the servo to set itself to the correct position. Okay, whatever you have sent here, okay, whatever the positive pulse you have generated here, to set to that position, you had to send at least 20 cycles of this pulse. Okay, that is what it says, but 50 is what recommended. 50 means 1 second. You are sending the pulse for 1 second, so it will set by the time it will be set to that particular angle. Okay, now I'm waiting for 1 second. This is a test code, so that I'll know the servo is sweeping from 0 to 0 to 90 degree. Okay, I mean, sorry, 1 millisecond to 2 millisecond, whatever I'm generating, it is sweeping from 0 to 180 degree. That is what I'm trying. So I'm just making a delay. Okay, and again it will come here and increment. Okay, so this for loop, I'm actually increasing the actually I'm increasing the positive pulse. Okay, so the I which is here, it is varying from 10 to 19. That means I'm generating 1000 ticks to 1900 ticks. Okay, so that is it, that is the thing. And then I'm generating this delay as it is, and now if I upload this program, the servo has to go from 0 degree to 180 degree. Okay, the servo what I had, it used to work from 0 to 90 degree. That is fine, but that was a specification. Okay, this is it about all the delays. So I'll close the window here and I'll let me set up the hardware, and I'll show when I upload these these programs, how it works. Okay, yeah. Okay, here is the hardware setup. This hardware I have explained in my previous video, microcontroller basic connections. Okay, so this is the PIC18 which is connected to the MCLR, PGD, PGC, and voltage, that is positive and negative of the microcontroller. Okay, and this is connected to external power supply also. Okay, so let's upload the program. 1 second delay. Okay, so it is compiling, and XE8 is little slow. And sometimes this PIC18 also gives a lot of error. Okay, let us see if it okay, it is giving all the missing configuration settings error here, so using default and all. And okay, so I think as you could see here, the red LED blinking. Okay, that means it is writing the code inside the chip. Okay, now it is green, that means it is up and running. So okay, it's little messy here, and okay, let me remove the negative cable of this PIC18, and I'll connect an LED to D1 and okay, so the LED is connected to D1. Okay, this is, I mean, sorry, D0, that means port D, and the other side of the LED is connected to negative. Okay, let me power it up again. Okay, as you can see, it is generating a 1 second delay. Let me connect servo. Wait. Okay, this is the one, right? So let me compile this. So I'll run this. By the time I'll connect the servo, time it compiles, I'll show you the connections. So from the power supply, I have taken this two wires, that is positive and negative, that is 5 volts, and then the same D, that is D0 pin, I am connecting to servo signal pin. Okay, So this is the setup, and let's see how it works. Let me keep this to a side and let's see how much it has compiled and what's happening. Okay, so it gives me a warning message and you can see the red LED glowing. Okay, I think it has done with the programming. So I'll remove this ground pin. Okay, the problem was insufficient power supply. Okay, so I was using some 5 volt 700 milliamps power supply, I think. Okay, and there was no rating written on that. So right now I'm using 1 amp power supply from an adapter. Okay, so let's see what's happening. Okay, so it's still compiling and giving configuration, resetting and all. Okay, so that's a problem. If you don't have a proper power supply, servo won't work. Basically what happened is, whenever the servo servo started drawing the power, right? Okay, it's programming now. So whenever the servo started drawing power from the power supply, this used to get reset. The LED will go off and again on. So that was the problem. So the microcontroller used to reset. Now let's try connecting. Okay, now also it's the same thing. It is consuming a lot of power. Okay, now you can see the LED is blinking. That means whenever this servo draws power, it is resetting. Now that is why you're not seeing the sweep. Okay, let me switch back to one more power supply. Instead of changing the power supply, I have changed the servo itself, which is a low power servo. This is 4.8 kg cm. Okay, now if you see, the color coding is very different here. That is black, red and white. Okay, this has already started to work. Okay, let me switch off and switch it on again. Okay, as you can see, it is rotating from left to right. That means 0 degree to 90 degree. So that was the thing. And generating delay using this method, okay, doesn't give you enough accuracy with respect to the pulse generated. That is a problem. Okay, so let me show you one small example. Please make note, it is rotating only to this corner, that is towards this wire. Okay, let me increase the range and let's see what happens. Okay, so here is the thing, I'm increasing the range here to 21, let's say 21. Okay, and then again I'm running this. This kind of boards are little messy. You had to keep connecting and disconnecting the line sometimes. And I don't know, for some reason PIC18 doesn't accept this voltage. I mean, like, it doesn't directly program. You had to supply a external power supply and then only program. Some glitches will be there, so be patient, and let's try this. Okay, so now it is programming. You can see that red LED blinking, and once it comes to green, that means it has programmed. See, such small glitches will be there, so just make sure you are doing this connections properly. And yeah, PIC18 requires external power. I mean, you have to connect your okay, wait, I haven't. Okay, now if you remember, I have extended the range a little bit. Okay, so now you can see it has reached till here, till that wire. Okay, so those things, if you experiment and write all those codes, it will work perfectly. So yeah, see you later. Bye.